Today we want to demonstrate the principle of conservation of energy for a case in which both mechanical and thermal energy are involved. Ordinarily, we'd go to a laboratory to do this, but we're not going to. We're going to use this commercial power plant as our laboratory. Let me introduce Arthur LaCroix.
I'm standing on the roof of the New England Electric System plant at Salem, Mass. The main building here is 15 stories high, and those stacks up behind me are 250 feet high. Over here is Salem Harbor, and that coal boat that's coming down the harbor now is going to unload at our dock. But we'll see a little more of that later. Over here are the coal yards, the coal storage pile, the oil storage tanks, and just beyond the stacks, the electrical switch yards and transformers. Now, the reason for this plant's existence is quite simple. Here we convert the potential energy of a fuel, such as coal, into random thermal energy, and that random thermal energy into a convenient and useful form, electricity. Now, in order to start the process, we must have a fuel. And as you may have already guessed, we need a large amount of it. In this plant, we can burn either coal or oil, but since it's a little easier to follow the coal and a little more interesting, we're going to talk about coal alone. The coal boat is about ready to land. Let's go down there now, where Charlie Sokolowski will explain the coal unloading process to you.
The ship being tied up at the dock is carrying 24,000 tons of coal and can be unloaded in about half a day. As the coal is unloaded from the ship, it is dumped on our active pile. In addition to this, we have a reserve pile which contains 170,000 tons. You might say we keep this for a rainy day. An interesting feature is that this coal does not lose any of its potential energy if properly stored. They're ready to unload now. Watch. The electrically operated boom, 250 feet in length, swings into position. In the next minute, 60 tons will be unloaded. At the bottom of the ship are conveyor belts that bring the coal from the hold up to the boom and then deposit it here on the pile. Each pile will be 40 to 50 feet high. From here, it will be carried up that conveyor chute to a crusher, where it will be reduced in size to about 1 inch in diameter. The crushed coal then continues up the chute and into the plant, where it is stored in bunkers until ready for use. We burn it at the rate of 100 tons per hour for the entire plant. For this film, however, we'll only study one of the 3 units in the plant. Now let's see how the potential energy of the coal is converted into random thermal energy and then into electrical energy, and how much of this potential energy, if any, is lost during the conversion process. But before you do that, you'll have to know a little of what the process consists of.
Power plants such as this consist of 6 important parts: a boiler, stack, a turbine, a generator, a condenser, and the public. Now let's take a little bit closer look at the process. Coal is stored in the bunker here and flows down into a pulverizer, from which it is removed and blown into the boiler, where it burns. Now, the boiler is nothing more than a box made up of a number of water-filled tubes that completely surround the furnace area. As energy is released in the combustion process, it flows through the tubes into the water, causing it to boil and vaporize. Incidentally, the water that we use in the boiler is the same as you and I would drink, with the exception that we have to purify it a little bit more in order to prevent the formation of scale inside the tubes. Steam leaves the boiler at 1,000 degrees and flows into the high pressure end of the turbine. The steam enters the high pressure blades here and flows through them, causing the shaft to rotate. Now, as the steam comes through, it's giving up some of its energy, doing work, and consequently it becomes cooler. So at this point, we remove the steam and bring it back to the boiler, where it is reheated and again leaves at 1,000 degrees and flows to the intermediate pressure section of the turbine. It re-enters the intermediate pressure section here and flows through the blades, and the shaft, of course, continues to rotate. From there, it flows to the low pressure section and finally exhausts to the condenser. Now, the condenser is just a box full of tubes with seawater flowing through them. And as the hot steam flows over the outside of the surface of the tubes, it gives up some of its energy to the water and is condensed back to a liquid form. At this point, it is picked up by a pump and returned to the boiler for reuse. Now, the turbine is coupled directly to the generator, which is producing the electricity which is being shipped to the public. Now, as we go through the plant, we're going to use this chart to account for the flow of energy in the process. The first stop will be the laboratory, where John Oliver is going to explain fuel analysis to us.
Here is a representative sample of coal, which you saw received a while ago. In the lab, we analyze the coal for the following things. First, the amount of moisture that's available in the coal when it comes over on the belt. Second, the amount of ash. And third, and most important, is the amount of total energy available when the coal is burned. We also do other tests, but we are not interested at this time with these tests. Now, let's see how we determine the amount of energy available in a given amount of coal. Approximately a gram of the sample has already been weighed, dried, and pulverized. The sample is put into a steel bomb. The bomb is charged with oxygen. Electrical leads are attached and the bomb placed in a pot of water inside an insulated jacket. The cover is put on and a stirrer and thermometer inserted. The bomb is ignited by an electric spark. As the coal burns, the energy released raises the temperature of the water in the pot. By watching this thermometer, you can see the temperature skyrocket. We are going to use the heating of water as a measure of energy. You know from experiment, the amount of energy required to heat water is proportional to the amount of water used and to the change in temperature. The amount of energy required to raise 1 pound of water 1 degree Fahrenheit is called a BTU. And this is the unit of measure that we'll base our calculations on. What did you get for a heating value of this sample?
13,500 BTUs per pound.
We burn 54,000 pounds per hour. This amounts to 729 million BTU per hour. This is the total energy supplied to the boiler.
Let's put on our chart here the 729 million BTU per hour, which is supplied to the boiler. energy is going into the boiler here in the form of pulverized coal mixed with air and burned in the furnace section. With the chemical analysis of the coal, we can calculate the exact amount of air required for combustion. But experience has shown us that we need to add some excess air in order to ensure that each particle of carbon will come into contact with oxygen. Looking in here, we can see the coal mixed with the air actually burning in the furnace. When we add excess air to this process, we're adding nitrogen, oxygen, some other inert gases, and some moisture in the air. All of these absorb energy and actually pass up the stack. Let's look now at a breakdown of the energy that passes out through the stack. The dry gas, which is actually the carbon dioxide and the nitrogen, accounts for 34 million BTU per hour. The hydrogen, which burns to water, and the water in the fuel, accounts for 26 million BTU per hour. The moisture in the air accounts for 2 million BTU per hour. The unburned carbon, 4 million, and the radiation, 3 million BTU per hour. This gives us a grand total of 69 million BTU per hour. Let's mark this down now on our chart and show this passing out of the stack. 69 million BTU per hour. Now actually, not all of these losses go out the stack. The radiation comes out through the walls of the furnace or through these pipes, and we can actually feel it. The unburned carbon, we take precautions to be sure that it doesn't get to the atmosphere. This is for obvious reasons. Let's go now and find out how much useful energy we can get out of this boiler. These instruments here show us how much steam is leaving the boiler and how hot it is. Here we measure the flow. Over here the temperature. And over here the pressure. Now by a simple lab experiment in which a given amount of steam heats up a known amount of water, we can determine how much energy is in the steam. Our readings here and some simple calculations indicate that 659 million BTU is leaving the boiler in the form of steam. Let's show that here on our diagram. 659 million BTU per hour. By adding up 69 million BTU per hour that went out of the stack and the 659 million BTU per hour, we get 728 million, which agrees very closely with the 729 million BTU put into the boiler. So far, there's been a conservation of energy. Remember now, up to this point, there has been no mechanical energy. Let's follow the steam and see where it goes. In order to demonstrate how hot the steam is, we've cut away a piece of insulation from the main steam line leading from the boiler to the turbine. Watch what happens if we place a broom against the exposed portion of pipe. Steam flows to and from the turbine through these pipes. They're well insulated in order to minimize the loss of energy into the room. The center pipe brings steam from the boiler to the high-pressure section of the turbine. Two others bring steam from the turbine back to the boiler for reheating. And the last two bring the steam from the boiler and return it to the intermediate section of the turbine. Now the control of the steam between the boiler and the turbine is handled in this room. Most of the operations are automatic, but can be done manually when necessary. These instruments control the flow of steam to the turbine and back to the boiler for reheating. The energy used for this reheating has Now remember, the condenser is just a box full of tubes with the cold seawater flowing through them and the steam flowing over them. Circulating water pumps force seawater through pipes under the floor and into the condenser. Now seawater at the rate of 30 million pounds per hour, and that's the flow you'd find in a good-sized river, is pumped through these pipes into the condenser. Over here, I can read its temperature at 60 degrees. Now, as the seawater goes through the condenser, it's picking up energy from the condensing steam. And then finally flows out the back end of the condenser and returns to Salem Harbor. Over here, we can read the temperature of the water as it leaves, and we find that it's 72 degrees. Remembering that if we know the pounds per hour of water flowing and the temperature rise, we can calculate the energy that goes into the water. In this case, we have 30 million pounds per hour of water flowing, and we have a temperature rise of 12 degrees. By multiplying the two, we get 360 million BTU per hour, which is flowing out into Salem Harbor. We had 659 million BTU per hour, leaving the boiler as steam. We're throwing away to Salem Harbor 360 million BTU per hour. The rest of the energy should show up as electrical energy out of the generator. Let's go and find out if this is true. Now remember, the turbine is coupled to the generator at this point. The electricity produced is carried away on cables which pass down through the floor out to the electrical switchyard. Over here in this room, we monitor the electrical output of the unit. Now these meters over here show the load on the machine. We find that we have 85,300 kilowatts on this unit. Now, if we generate at this load for 1 hour, we will produce 85,300 kilowatt hours. We read that on this meter here. It's the same kind of a meter you would have in your home. Now, it's easy enough to convert kilowatt hours to BTU. We could do this on a small scale by immersing an electric heater in a beaker of water and watching the temperature rise. And if we did do this, we would find that 1 kilowatt hour is equal to 3,413 BTU. Now, multiplying the 85,300 kilowatt hours by 3,413 BTU, we find that we have 291 million BTU per hour coming out of the generator as electricity. Let's put that on our chart. 291 million BTU per hour. Now let's see how our books balance. Coming out of the stack, we have 69 million BTU per hour. Leaving the boiler, we have 659 million BTU per hour, but that was accounted for in these two figures. Out of the generator, 291 million BTU per hour as electricity, and thrown away to Salem Harbor, 360 million BTU per hour. And adding them up, we find that we have 720 million BTU per hour. which compares quite favorably with 729 million BTU per hour, which we put into the process, within 1.25%, which is about all that we can expect from our instrumentation. There remains just one thing for us to do now, and that is to get the electricity to you. We started on its way here through our electrical switch yards. These transformers step up the voltage for more economical transmission, but they don't add any energy and waste very little. Circuit breakers connect the electrical output of the plant to the distribution system. In addition, they act as a safety device. If there is a short circuit on the transmission lines, these breakers open and disconnect the plant from the line. The electrical energy then goes out through underground cables and over high voltage lines to substations and then to you, where it is available for conversion to a direct mechanical form.
Now, the process naturally breaks up into two parts. The first part involves no mechanical energy at all. Energy contained in a mixture of coal and air fed into the furnace. Part of it goes up the stack, and part of it comes out of the boiler in the form of hot steam. The book's balanced, but no mechanical energy was involved. The second part of the process involves mechanical energy in electrical form. LaCroix said that 659 million BTUs per hour came out of the boiler hot steam. How did he know that? Well, it's easier for him to make the measurement than it would be for us. Because in order to make that measurement, the steam has to be at 1,000 degrees Fahrenheit. That's red hot. And at 1,450 pounds per square inch, that's almost 100 atmospheres. And you have to condense that steam to water at room temperature. And in doing so, you have to make sure that you haven't used any of the energy on some other form, say mechanical form. All of the energy has to go directly into heating up some other water for the purpose of making the measurement. Now, knowing the total amount of steam that passes through the system and the amount of energy that it would liberate in a sample, you calculate this 659 million BTUs per hour. Now about the electrical part. We said that that was available for conversion to mechanical energy, and we only meant that we could take the 291 million BTUs per hour and use it for running an electric train or turning refrigerator motors or spinning electric fans. But in fact, we measure the amount simply by heating up water again, by a straight thermal process. Now let's consider the steam that goes into the condenser. You might ask two questions. Why do we condense the steam to water? And why do we throw all of that energy into Salem Harbor? The two questions have the same answer. We have to reduce the back pressure against the turbine blades. For the same reason that you have an exhaust pipe on an automobile. You have to let the exhaust gases escape through the exhaust pipe. In this case, the best way to reduce the pressure is to condense the steam to water at a low temperature and at a low pressure. But in order to condense the water, we have to extract energy, and that turns out to be a total of 360 million BTUs per hour. The sum of these two, 651 million BTUs per hour, is to be compared to the 659 million over here. So we see that the books balance in the second part of the process. We've shown that the principle of conservation of energy holds here too. But what the engineers want to do is something a little different. They want to get as much of the energy as they can into organized form, into electrical energy, and to waste as little as need be heating up the harbor. They do this very well. But for our purpose, we wanted to use this large plant in order to show that the principle of conservation of energy holds for a simple practical, large-scale operation.